You open Facebook, your feed loads in under a second. But in that second, Facebook made thousands of personalized decisions just for you. You have 500 friends. They posted 1,500 times this week. Facebook showed you maybe 25 of those posts. How? A 4-stage ML pipeline ranking 100 billion posts daily. In 2018, one single tweak to this pipeline reduced passive video consumption by 50 million hours per day. This is not a simple sorting algorithm. This is one of the most complex real-time ML systems ever built at scale. Let's put this in perspective. Facebook has 2 billion daily active users. Each user's feed pulls from roughly 1,500 candidate posts per load. Multiply that out, 3 trillion ranking decisions every single day. Tau, Facebook's social graph cache, handles 1 billion read operations per second just to fetch those candidates. A single newsfeed ranking model retraining cycle processes 1 petabyte of interaction data. That takes 4 hours on a 1,000 GPU cluster. This isn't big data. This is a category of scale most engineers never encounter. But here's the catch. All of this must complete in under 200 milliseconds per feed load. Think of a chronological feed like a group chat where one person texts every 5 minutes. Their messages bury everyone else's. That's exactly what happens without ranking. One prolific friend posts 20 times a day and dominates your entire feed. Pure engagement optimization is even worse. Facebook measured this in 2019. Raw engagement signals trained their own models to recommend increasingly sensational content. Their internal 2018 study, later leaked by Frances Haugen, showed ranking algorithms were actively pushing users toward extremism. Relevance without constraints defaults to outrage. This is why ranking exists, not just for personalization, but for platform health. Before ranking a single post, Facebook must decide which posts even qualify. A user with 500 friends, 20 followed pages, and 10 groups has an enormous candidate pool. Fetching every historical post from every connection is impossibly slow. Facebook solves this with Tau, the Associations and Objects system. Tau is a distributed social graph cache storing friend edges, follows, and group memberships entirely in memory. A single feed load queries Tau for posts from first-degree connections within the last 7 days. Result: roughly 1,500 candidates retrieved in under 10 milliseconds. Sources break down as 40% friends, 30% groups, 20% pages, and 10% ads. Now here's where it gets interesting. Ranking those 1,500 posts happens in 4 distinct stages. Facebook's pipeline is a funnel. Each stage cuts the candidate pool aggressively. Stage 1. Tau retrieval returns 1,500 posts in under 10 milliseconds. Stage 2. Light ranking runs a gradient-boosted decision tree, GBDT, on all 1,500 posts. Inference is under 1 ms per candidate. It eliminates obviously irrelevant posts, passing 500 forward. Stage 3. Heavy ranking runs a deep neural network using 2,000 features per post-user pair. GPU-optimized inference runs in under 300 microseconds per candidate. Total latency for 500 candidates under 150 milliseconds. Stage 4. Contextual re-ranking applies diversity rules, integrity filtering, and ad injection. Final feed emerges in under 20 milliseconds. Total end-to-end under 200 milliseconds. Facebook doesn't just optimize for likes. Think of it like a court scoring Olympic gymnastics. Different judges score different dimensions, then one final score combines them. Their heavy ranker is a multitask learning network with separate prediction heads per action, like weight 1x. Comment 4x, it's a meaningful social interaction signal. Share 8x, the highest viral indicator. Hide, negative 10x. Report or unfollow, negative 50x. These probabilities combine into one value score per post. Critically, the weights are not hand-tuned by engineers. They're learned via reinforcement learning targeting 28-day user retention, not just session engagement. That distinction separates Facebook's model from pure click-through rate optimization. Here's what the value score computation looks like in practice. The model produces a probability for each action type: like, comment, share, hide, unfollow, and video completion. Each probability gets multiplied by its learned weight. Negative actions subtract from the score. The final value score determines the post's rank position. Notice the weights here: comments at 4x, shares at 8x, hides at negative 10x. In production, these weights are not hard-coded. They're output by a reinforcement learning optimizer targeting long-term retention metrics. But this structure captures the essential logic. This is why a post with 10 comments outranks a post with 100 likes. This is why engineers lose sleep over weight calibration. The heavy ranker ingests 2,000 features per post-user pair. They fall into 4 buckets. Affinity signals. How often have you interacted with this author in the last 30, 90, and 365 days? Mutual friends. Message frequency. Profile view rate. Content signals. Media type. Video gets a 2x base weight. Post age with a 6-hour half-life exponential decay. Engagement velocity. How fast is this post collecting reactions right now? Context signals. Your device type, connection speed, time of day, and session length so far. Historical performance signals. This author's average engagement rate across their last 100 posts. Features update at 2 cadences. Hourly batch via Hive, and real-time per event via Scuba and Memcached. Real-time features catch the going viral signal that batch processing always misses. Between heavy ranking and your feed sits an integrity filter. Think of it like airport security. Every bag goes through the scanner, not just the suspicious ones. All 300 ranked candidates get scored by independent ML models. Hate speech detection uses a transformer-based classifier trained across 200+ languages. Meta's 2023 transparency report shows it catches over 99% of violating content before any user report. Misinformation gets cross-referenced against third-party fact-checkers via a dedicated key-value store lookup in under 100 milliseconds. Spam detection uses account-level signals, post frequency, account age, and IP reputation. Flagged posts are demoted, not deleted. Their score gets multiplied by a penalty between 0.01x and 0.5x. Hard removal requires human review. This entire layer adds under 15 milliseconds to feed latency. The top 300 posts pass through one final re-ranking step. 2 goals here. First, diversity. Without enforcement, your most engaged friend dominates your entire feed. Facebook caps consecutive posts from the same author at 2. Same content type, all videos for example, caps at 3 consecutive. Implementation is a simple greedy scan with author and content type frequency counters. No fancy ML needed here. Second, ad injection. Facebook's ad auction runs in parallel with organic ranking. Ads land at positions following a roughly Fibonacci-spaced pattern, positions 3, 7, 13, 21. They're inserted as pinned slots. They don't displace organic content. They inject into pre-reserved positions. This merge step is the last thing that happens before your feed renders. Instagram runs 2 completely separate ranking systems. Home feed works like Facebook's pipeline. Social graph constrained, friend first. Explore is an entirely different problem. It has no social graph constraint at all. It recommends from 500 million public posts using embedding similarity search. Think of it like Spotify's Discover Weekly. It finds content you'd love from people you've never followed. Explore's heavy ranker uses a 2-tower neural network. One tower encodes the user's interest embedding. The other encodes the post's content embedding. Approximate nearest neighbor search finds the best matches in milliseconds. This is why Explore feels like TikTok, because architecturally, it is. LinkedIn uses an identical 2-stage approach for their feed, adding a professional context signal called virality score. Here's what the final diversity re-ranking step looks like in production. We iterate through the heavy-ranked posts in order. We track consecutive author counts and consecutive content type counts. If either exceeds the cap, 2 for authors, 3 for content types, we skip that post and try the next candidate. Skipped posts get placed later in the feed, not dropped entirely. This greedy ON scan is intentionally simple. Facebook engineers chose simplicity here. The ML complexity happens upstream in heavy ranking. The diversity layer just enforces constraints on the output. Notice how ads are injected at Fibonacci-spaced positions as a completely separate merge step. No interference with the organic ranking logic. Facebook's newsfeed is a 4-stage funnel. Tau graph traversal retrieves 1,500 candidates in under 10 milliseconds. GBDT light ranking cuts that to 500 in under 20 milliseconds. A deep neural network with 2,000 features scores the top 500 in under 150 milliseconds. Integrity filtering and diversity enforcement produce your final feed in under 20 milliseconds more. The value score is not a like counter. It weights comments 4x, shares 8x, and applies brutal negative penalties for hides and unfollows. Weights are learned by reinforcement learning targeting 28-day retention. Diversity enforcement is a simple greedy scan. The ML complexity belongs upstream. And the integrity layer processes every single post, not just flagged ones. 3 trillion of these decisions happen every day. Facebook's feed isn't magic. It's a disciplined 4-stage ML funnel with hard latency budgets at every step. The real insight: simplicity lives at the edges, greedy diversity scans, and complexity lives in the middle. 2000 feature neural networks. Next video, how TikTok's For You page recommendation engine works without a social graph at all. Subscribe so you don't miss it.